Welcome back. Let's purchase a few more tools for our tool belt. So the limit as x approaches positive or negative infinity of a constant. What do you think that's going to be? Yeah, it's just going to be that constant. Remember, the constant is just a horizontal line, and so if you take the limit as x approaches positive or negative infinity or any particular number, it's just going to still be that constant. The constant is not affected by what the x values are doing. It doesn't really care what x is doing. Now let's look at the limit as x approaches plus or minus infinity of 1 over x. What do you think that's going to be? If you said 0, that would be correct. The idea here is that if x is approaching positive infinity, let's say, then the x values are going something like maybe 10, 100, 1,000. We could write 1,000,000. Now, why am I writing 1 over these? Because we have 1 over those x values that are approaching, that are getting bigger and bigger and bigger. So we're plugging into the x like 10, 100, 1,000, million, and so on. So those fractions keep getting smaller and smaller and smaller, getting closer and closer to 0. A way of summarizing that would be to say that 1 over a big number is going to be a small number. In the same way that 1 over a small number is equal to a big number. So it's like an analog or a parallel to the limit as x approaches 0 of 1 over x. All right, what about the limit as x approaches plus or minus infinity of 1 over x squared? If you said that's also equal to 0, then that would be correct. Because, again, the bottom is blowing up to infinity, so 1 over that is going to be shrinking down to 0. Just think about in your head these fractions that just keep getting to be smaller and smaller fractions. The bigger the bottom gets, the smaller the overall fraction is going to be, closer and closer to 0. And it doesn't matter if these are signed negative, it would still be the same thing. Let's use these tools to evaluate these examples where we have limits with x approaching either positive or negative infinity. So in this case, we have x approaching positive infinity. Now, if we think about what the top and the bottom are doing separately, well, the top is getting to be bigger and bigger. It's approaching infinity. And the bottom is also approaching infinity. So you might say this is like an infinity over infinity kind of situation. This is one of the indeterminate forms, just like 0 over 0 was. What we can do to evaluate this, because, I mean, clearly just plugging in infinities is not going to help us out. What we can do to evaluate this, there are different ways of handling it, but one way is to take the top and the bottom and divide by the leading term, or the leading variable part of the bottom. So in this case, by the x squared. What that's going to do is it's going to allow us to make the bottom approach something that's not 0, and then finish evaluating the limit. Let's see what happens. So actually, I'm going to do this down here. We're going to divide everything on top by x squared. Everything on the bottom by x squared. And I'll write the note off to the side real quick. There it is. Divide the top and the bottom by the highest degree term of the bottom. And I didn't really write it here, but you don't have to include the coefficient in front. You could, but it just makes things a little bit more messier. You don't need to include the coefficient, just the highest degree term without the coefficient. So in this case, it would be x squared. So that's the highest degree term of the bottom. And then when you simplify, you're going to see something happening. 6x squared divided by x squared, that gives you 6. Then you have an x canceling with the next term, and you get 9 over x. The last term just stays as negative 1 over x squared. And then on the bottom, you get 3 plus 4 over x squared. So what happened is we turned this limit, we turned the fraction into a bunch of these little fractions on top and the bottom of the big fraction. So we turned them into like 1 over x type things. It's 9 over x, but you can think of it as like a 1 over x with just a 9 coefficient in front. So it turns it into these little limit as x approaches infinity of 1 over x's, or 1 over x squareds. So we can use these tools that we just purchased with our hard-earned money. And so those little fractions, the ones that have the x's on the bottom, those are going to go to 0 as x approaches infinity. When x gets really large, those fractions are going to shrink down to 0, because 1 over large numbers are going to be going to 0, or even 9 over large numbers are going to be approaching 0. Even if you had a big number on the top, like a gazillion, if that were a number, divided by x, eventually that would shrink down to 0, because x is approaching infinity here, and that's bigger than any number. I mean, it's not a particular number, it's just an idea of numbers getting bigger and bigger and bigger, and eventually you're going to pass whatever the number is on the top. And so these fractions will eventually shrink down to 0. So then the 1 over x squared, that's also going to approach 0. The 4 over x squared is also going to approach 0, because again, if the bottom blows up to infinity, the overall fraction shrinks down to 0. So what you have left on the top is 6 plus 0 minus 0 over 3 plus 0. Notice I've written this limit as x approaches infinity, and then written it again, and then I stopped writing it. So why did I stop writing it at this point? Well, because my hand got tired. No, just joking. I stopped writing it because here, from this step to this step, I lost all the x's. The x's are gone now from the picture. I've already went through the thought process. What if x goes to infinity? Well, this whole thing is approaching 0. So I don't have if I'm not writing the x's anymore in my expression, I don't need the limit as x approaches infinity. Or if I plugged in x equals something to take the limit, then I wouldn't need to write the limit anymore. If I've taken the limit, I don't need to write it anymore. So when the variable that you're taking the limit of, or the variable that is being used in the limit, if that one disappears, then you don't need to write that limit anymore. But up until that point, you will have to make sure to write that limit, because that's an action that's waiting to be done. All right, so this evaluates to then 2. You can check in the picture as well. So here's the graph of that rational function. If you take the limit as x approaches infinity, the y values seem to be getting closer and closer to a y value of 2. And as a reminder, that informs you that you have a horizontal asymptote, y equals 2. So taking this limit as x approaches infinity of our function and getting 2 tells you that this function has a horizontal asymptote y equals 2. For example 15, we have the limit as x approaches negative infinity of 25x plus 3 over 2x cubed minus x plus 1. Now if we think about what's happening to the top and the bottom, again, the top is approaching some kind of infinity. In this case, it's a negative infinity, because if you plug in large negative numbers, the 25x becomes a really large negative number, overshadowing the plus 3 by a lot. On the bottom, the same kind of thing will happen. The 2x cubed is the leading term of the bottom. That's the one that's going to run the show of the bottom numbers and overshadow the rest of the smaller terms when x gets really large, even in the negative direction. And since that's going to be a negative number, when you take negative to the third power, it's negative times positive 2 is still negative, so the bottom's approaching negative infinity as well. The negative actually doesn't really matter too much for our purposes here, but I'm just doing that analysis to help you think through that process. Okay, so the key thing is that this is an indeterminate form. It's some kind of infinity over infinity. So our strategy is going to be to divide the top and the bottom. Divide the top and the bottom by the leading term of the bottom. So that's going to be the 2x cubed, but I'm just going to write x cubed because I don't need to divide by that coefficient. So now we're going to have 25x divided by x cubed. That'll give us 25 over x squared plus 3 divided by x cubed over, and then on the bottom we'll have 2 minus, whoops, the x will cancel with the x cubed and give us 1 over x squared plus 1 over x cubed. Now all these little fractions with the x's on the bottom, or the x squareds, the x cubes, all those are going to 0 as x goes to negative infinity. Positive infinity or negative infinity, those little fractions with numbers on the top and x's raised to powers on the bottom, those are all going to go to 0. So if you look at what's left over on the top, it's just 0. You have like 0 plus 0, which is 0. And on the bottom you have, oops, 2 minus 0 plus 0. So this is 0 over 2, which is 0. Yep. When the 0 is over, the answer is 0. And that's what we're seeing on the picture to the right. If we let x go to negative infinity, the graph is getting closer and closer to 0. So we have this horizontal asymptote. Y equals 0. Looking at example 16, we've got the limit as x approaches infinity of x squared minus 1 over x plus 2. So once again, we can think what happens to the top and the bottom. When x approaches infinity, the x squared is going to infinity, and that overshadows all the rest of the terms on the top. When x goes to infinity, the x is going to infinity. So this is an infinity over infinity kind of limit. This is another indeterminate limit. And we have our technique for handling it. We'll take the top and the bottom, divide by the leading term of the bottom, which here would be just x. And it doesn't have any coefficients to worry about. And even if it did, we wouldn't worry about them. So here you have x squared divided by x, which is x, minus 1 over x. And then x divided by x is 1, plus 2 over x. Okay. So now, we'll take stock of our situation. We know that 1 over x is, oops, let me switch over to this other color. So we know that 1 over x is going to be approaching 0. And 2 over x is approaching 0 as well. Not sure why it's smeared like that. Draw that again. But then if we think about what's happening on the top now, I'm going to do a little analysis off to the side. The x is approaching infinity, so this part of it is approaching infinity while the 1 over x is approaching 0. So what is the top approaching overall? If you said infinity, that would be correct. These large numbers, larger and larger numbers, are just blowing up to infinity, and these minus numbers close to 0 are not really doing anything else, not really doing anything, or less and less at least. So the top is being dominated by this x right here, which is going to infinity. What about the bottom? What is the bottom approaching? If you said 1, that would be correct. It's 1 plus these numbers getting close to 0. So overall, the bottom is approaching 1. So overall, what would you say the numbers of these fractions are doing? Correct answer would be infinity. These are overall going to infinity. The numbers on top are blowing up to positive infinity. The numbers on the bottom are getting closer and closer to positive 1. And when you divide those two, you just get these numbers that are blowing up to positive infinity. Positive because it's a positive divided by positive, which gives you positive. All right, so there's what the analysis looks like in example 16. Now, one common question is, why don't we just divide top and bottom by x squared? Wouldn't that be easier? Like, because that's kind of the leading term overall. Like, why do we have to divide by the leading term of the bottom? And the short answer, or one answer, is that when you divide the top and the bottom by the leading term of the bottom, it makes it so that the bottom is approaching a non-zero number. In fact, that non-zero number that it's going to approach is going to be whatever the coefficient of that leading term is. So notice it was 1 in this case. In the other examples, the bottom became 2. And all these other things that had smaller degrees, those all went to 0. notice for the example before that, example 14, the bottom became the coefficient of the leading term there, which was 3. It became a 3 because all those other little fractions went to 0. And that's nice for our analysis. It's nice that the bottom goes to a non-zero number, because if the bottom did go to 0, now we've got a bit of a headache on our hands, because now we have to think, is that going to 0 from the positive side? Is that going to 0 from the negative side? Because that would make a difference, you know, overall with our numbers. It would tell us if our numbers are going to be positive or negative. So to not have to do that, it's more helpful to divide top and bottom by the leading term of the bottom than of overall the top and the bottom. Like if we were to divide the top and the bottom here by x squared, for example, just to follow this through, if we were to divide by top and bottom by x squared instead, we would have 1 minus 1 over x squared over 1 over x plus 2 over x squared. Now the top would be not too bad to analyze. The top would be going to 1, but the bottom, that would be approaching 0. The 1 over x goes to 0, the 2 over x squared goes to 0. The bottom would be approaching 0, but then you'd have to think, all right, is this positive or negative? And well, for this particular example, it's pretty clear that it's positive because everything that we're dealing with is positive here. But if this were like a minus in between, then it's harder to figure out that analysis. So while we could have done it either way for this particular example, you want to think instead just divide top and bottom by the highest degree term of the bottom. All right, so we'll end this part here, and then we'll continue on in the next part. Thanks for watching.